Screen share. All right, how is everyone today?
Staying warm.
Awesome. Yeah, it's interesting out there. All right. Well, we got 2 weeks of school left, so we have 4 classes left until the end of the quarter. So, I will post homework on Wednesday, and that homework will be for the unit we're finishing today, which was the unit on counting, as well as the unit we're going to start either today or Wednesday, which will be automata theory. And that'll be the last homework assignment for the course, and that'll be due a week from Wednesday, which will be our last class. So I'll grade it and post feedback on it before the exam. But we're getting to the end of things pretty quickly. So any questions from last time? We were talking about product rule and sum rule, and then the principle of inclusion exclusion, and then we switched to talking about the pigeonhole principle, and that was I think where we left off. So we had talked about the pigeonhole principle. There's a generalized version of that called imaginatively the generalized pigeonhole principle, and it's basically the same idea, but in a more general form. So remember, the pigeonhole principle basically says if you have k boxes. All right, let me give it up on that for now. If you have k boxes and k plus 1 items, and you try to put those items into those boxes, you have at least one box containing at least 2 items, right? And you could have, one box containing all the items. You could have each box containing 1 item, and one box contains 2 items. All it's saying is that, no matter what you do, you cannot arrange things so that that you don't have at least one box with 2 items in it. So you're going to have to double up at least one spot. And so the generalized pigeonhole principle says the following. If you have n objects and you have k boxes, and you try to place those objects into boxes, at least one box has at least what we call the ceiling of n over k items. And the ceiling is an operator. It's kind of like rounding, but a little bit different. The ceiling of x equals the smallest integer bigger than or equal to x. So if x is an integer, the ceiling is just x. But if x is an integer plus a little bit more, it's the first integer you find that's bigger than or equal to x. And so, for example, the ceiling of 2 is 2. The ceiling of 2.01 is 3. That's the smallest integer, bigger than or equal to 2. The ceiling of 2.5 is 3. The ceiling of 2.999 is still 3. And the ceiling of 3 is 3. But the ceiling of something just a little bit bigger than 3 is going to be 4. All right, so this may be a new operator to use. Ceiling of x is the smallest integer bigger than or equal to x. And so the generalized pigeonhole principle says if you have n objects in k boxes, at least one box has ceiling n over k items in it. So if our number of objects is k plus 1, the generalized pigeonhole principle tells us that at least one box contains at least this many items. And if k is a positive integer, ceiling of k plus 1 over k is always going to be k plus 1. So the pigeonhole principle that we sorry, this is equal to 2. So the pigeonhole principle that we talked about last week, k plus 1 items, k boxes, comes from the generalized pigeonhole principle, right, which would tell us at least one box has at least 2 items in it. But this is a more general form, and it's sometimes more useful. So for example, 25 people and 7 days per week. So the generalized pigeonhole principle tells us that at least this many people were born on the same day of the week from a group of 25. And how do we know? We'll make 7 boxes, one for each day of the week, put those 25 people into those boxes based on the day of the week in which they were born. Generalized pigeonhole principle says at least one box contains at least this many items. Well, ceiling of 25 over 7, that's the ceiling of 3 4/7, which is 4. And so at least 4 people out of a group of 25 will have been born on the same day of the week. Which, you know, you might be able to figure out by playing with the numbers, but it comes directly from this generalized principle. Alright, here's another example. Suppose you have a deck of 52 cards. And cards are broken up into 4 suits: clubs, diamonds, hearts, spades. So you have 13 cards of each suit. And the question is, how many cards must you pick to guarantee that at least 3 have the same suit? And this is a sort of general form for these pigeonhole problems. And, you know, certainly if I pick all 52 cards, I'm guaranteed at least 3 of them have the same suit. In fact, if I pick 52 cards, I'm going to have 13 that have the same suit. I'm actually going to have 13 clubs, 13 hearts, and so on. But the more interesting question is, you know, what's the minimum number of cards I have to pick to guarantee that I have at least 3 with the same suit? And, you know, it could be I pick 3 cards, and I get a 2 of hearts, a 3 of hearts, and a 4 of hearts. I got 3 cards with the same suit, but that's not guaranteed. I could pick 3 cards and get, you know, a 2 of clubs, a jack of diamonds, and an ace of spades. So this question is really asking, you know, what's the minimum number of cards you have to pick to guarantee that you've got at least 3 of the same suit? And problems like this, right? Think about the pigeonhole principle. So here's clubs, here's diamonds, here's hearts, here's spades. And we're going to pick some number of cards and start putting them into here. So let's say we pick K cards. And for any positive integer k, if I pick k cards, how many am I guaranteed to have of the same suit? Well, generalized pigeonhole principle says that for k cards, if I put them into 4 boxes based on suit, I'm guaranteed at least one box has at least this many cards. So this question can be rephrased. Find the smallest k such that this is greater than or equal to 3. Well, the smallest k for which this is true will be the smallest k for which this is equal to 3. And so now I'm just looking for the smallest positive integer such that the ceiling of k over 4 is equal to 3. And that's something that we can trial and error. So find smallest k such that ceiling k over 4 equals 3. So what are some values for k? K equals 0. Ceiling of 0 is 0. If k is 1, 2, 3, or 4, ceiling of k over 4 will be ceiling of 0.25, 0.5, 0.75, 1. That's going to be a 1. If k is 5, 6, or 7, or 8, k over 4 is going to be 1 point something, 1.25, 1.5, 1.75, or a 2, this is going to be 2. If k equals 9, the ceiling of k over 4 is going to be ceiling of 2.25, smallest integer bigger than or equal to that, that's 3. And so that's your answer. If you pick 9 cards, you're guaranteed at least one box has 3 objects in it or more. And whatever box you're in, the fact that there's 3 cards in that box means those 3 cards have the same suit. So this is another set of questions for which we don't have, kind of a turn the crank formula. We have to think about what it's asking and then try to take something like the generalized pigeonhole principle, or maybe, the sum rule or the product rule or whatever else we've been talking about, and see how that applies to what we're being asked to find out. But most of the pigeonhole problems, they look a lot like this. They look very much like put things in boxes and then find typically the smallest number of something that guarantees some outcome. All right, so questions about that?
The third row, is that 5, 6, 7, 8?
Mm-hmm.
K equals 5, 6, 7, 8.
Yeah. And this is just, exploring what this ceiling function does. But in general, if you wanted to find a k so that ceiling was at least 7, right? So we want ceiling k over 4 equal to 7. Well, I'm probably just going to go with 28. Right, I'll try 28 fourths, and that's certainly equal to 7. And anything smaller than this, divided by 4, would be 6 point something. Well, that would also be a 7. And so I'll go down to, maybe 24 over 4. Well, that's a 6. But if I go up 1 from that, 25 over 4. Okay, so that's 6 point something, and the ceiling of that will be 7. So 25 would be my answer in this case. So this is a function that probably is relatively new to most of us, and so our intuition may not be fully developed for it, right? Rounding down, that intuition is pretty well developed. We learned that in elementary school, how to round numbers. But in this case, you're kind of rounding up, but not exactly, right? Because like 3.1 will suddenly round up to 4, but 3.0 stays at 3. So we're just playing with it to get a feel for it, see how it works. All right, other questions about that? All right, so we're going to go on to permutations and combinations. And we're going to start with permutations. We're going to define exactly what we mean by a permutation. And it's going to have a very specific meaning. And then we're going to talk about combinations, and that will have a very specific meaning. And those meanings may be different from what we're used to using when we talk about those, but we're going to want to know exactly what these things mean. And combination is going to be sort of backwards from what we think, especially if we're used to combination locks. So we're going to define these things very carefully. And this will be our last topics for this part of the course on counting. And then we'll go on to something else. But let's talk about permutations. And this will take us into some interesting things. So here's a definition. So a permutation is an ordered arrangement of items. And the ordered part is going to be key, because combinations will be exactly the same, but they'll be unordered. So a permutation is an ordered arrangement of objects. And more generally, an R permutation is an ordered arrangement of R items. So for example, suppose we have the set containing the elements A, B, and C. So we have three items. All right. A, C, B is a permutation of these items. ABC is a permutation. CAB is a permutation, and so on. So it's an ordered arrangement of items. AB is an example of a two permutation. So is BC, CB, AC, and so on. So any arrangement where the order is significant, we call that a permutation. All right, so more specific examples. So suppose we're given 5 students. And we want to put 3 of them into a line. So there's a line, there's a first position in the line, a second position, and a third position. The positions in the line are distinct from each other. We're not just putting 3 students into a group, we're putting them into an ordered line, right? And so this is a question about making a 3 permutation of 5 objects. And so a typical question is, in how many ways can we do this? In how many different ways can we put 3 students into a line out of a group of 5 students?
Something like, it's like 5 exclamation point over 3, or I don't remember the exact, there's a formula for it.
There is a formula for it, but even without knowing the formula, we should be able to answer this question using the product rule. So how can we think of this question of putting 3 students in the line as a succession of tasks? What would be the tasks we would do? This is definitely worth SpongeBob money. So what succession of tasks could we do so that the end result is that we've picked 3 students and put them into a line out of a group of 5? Say again?
Pick a student.
Pick a student, good. Task 1. Pick a student. Are we going to put them in the front of the line?
Sure.
Alright, pick a student for front of line. And then what's the second task?
Or I guess take. No. Yeah.
The second student for the second position.
Pick a second student for second position. And then the third task, pick a third student for the last position. If we do these 3 subtasks, we've completed the task of picking 3 students to put in a line. So how many ways can we choose a student from a group of 5 to go in the front of the line?
5.
Because we can pick any of the 5 students. And then how many ways can we pick a student to go in the second place?
4.
Right, because we've already picked one. And then to pick the last student, we've already picked 2 students. We've got 3 students left. So the number of ways we can do this is 5 times 4 times 3.
So it'd be 5 bang over 3 bang.
Close. It's actually over 2.
Oh, okay. 2.
Yeah, but we're going to do that right now.
Wait, 2 or 2 exclamation point?
Same thing, but technically 2 exclamation mark.
Same thing, but like if the numbers were different.
Yeah, exclamation mark.
Okay.
Yep. All right.
I don't know how to normalize saying bang. It's so much quicker.
Yeah. Exclamation mark. So before we do a formula, let's do some notation. So we'll have a general notion of p n comma r, and this is a function that means the number of r permutations of n objects. So the short answer to how many ways can we put these students in this order would be just p5 comma 3. And if you were with someone who spoke permutations, or if your calculator has a p button on it, right, this is the same answer as 5 times 4 times 3, which is 60, by the way. So p n comma r is our symbol for the number of r permutations of n objects. All right, so let's find a formula for this. And let's just go by example. A lot of discovery in mathematics builds out of examples. You do something with particular cases and you see a pattern, right? We're good at finding patterns. You find a pattern and then you get an idea and you form a hypothesis and say, oh, I think, maybe this formula is equal to such and such. And then you try to convince yourself it's real, and then you do an inductive proof to prove it, and then you're rich and famous. So let's just look at something like p 9 comma 4. All right, this is the number of 4 permutations of 9 objects. We're trying to pick 4 things out of 9, and the order is important. So we have 4 subtasks. T1 is pick first item. T2 is pick the second item. T3 we pick the third item. T4 we pick the fourth item. And pretty clearly, no matter what we're talking about, whether we're talking about students or elephants or chainsaws and torches, right? The way we break this problem down is going to be pretty much the same. We're going to, if we're trying to pick 4 objects, make 4 subtasks, where the first task is to pick the first item, the second is to pick the second, and so on and so forth. And the number of ways we can do this is going to look very similar. The number of ways we can complete the first task will be the number of items we have, which is 9 in this case. And since we're picking an item for task 1 and then we're doing task 2, we have one fewer thing to pick. So it'll be 8, 7, 6. And so in general, this is going to look something like this. And we can hypothesize that there's a pattern here. And there is a pattern. And eventually we could say something like, you know, P13, comma 5. Well, we're pretty confident that's going to end up being 13 times 12 times 11 times 10 times 9. So you're going to have 5 of these things. You're going to start from that biggest number and just keep going down by 1. And that is what the formula for P of n comma r will look like. It will just be, you know, n times n minus 1 times n minus 2, a total of r times. But we want to find an easier way to write that, and we can do that using factorials. And so we're going to do this trick that we do sometimes of multiplying by 1. So we're going to take 9 times 8 times 7, 6. We're going to multiply by 1. But we're going to do a particular version of 1. I'm going to multiply this by 5 times 4 times 3 times 2 times 1, divided by 5 times 4 times 3 times 2 times 1. Now everybody agrees this is equal to this, right? Because the thing in parentheses is just 1. And this is exactly the same as that.
No, I don't believe. No.
Okay. But this lets me, you know, draw my line over here, and this thing up here, how can I write this more concisely? Using maybe some kind of punctuation mark. Yeah, this is 9 factorial. 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. And how could I write the bottom similarly?
5 bang.
That's 5 factorial. Perfect. So, you know, there's a 9 right there. There's a 4. There's a 5. There's something similar going on here, right? Let's try another example. So, P9, comma 4. Equals 9 factorial over 5 factorial. Let's try P 9 comma 2. So, you know, 2 tasks. Pick the first person, we can do that 9 ways. Pick the second person, we can do that 8 ways. And I'm going to, again, multiply this by 1. And now the top is going to be 9 factorial, the bottom is going to be 7 factorial. So P9 comma 2 equals 9 factorial over 7 factorial. So who wants to hypothesize a formula for Pn comma r?
Well, I don't know. Is there a
Would it be,
n over r, n bang over r minus 1 bang?
So I like the n on the top. We got the 9 and the 9 and the 9 and the 9. And you know, we know we're going to multiply by 1. We're going to start with n. And so that's going to go on. The number of things we have on the bottom here, in this case it was r plus 1. In this case it's r plus 5. So we need a different formula for what's on the bottom.
Wait.
I was gonna say n minus r.
Ding, 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 ding. There you go. That turns out to be the right formula.
Oh.
N factorial over n minus r factorial. And if you try to do this in general, you have r of these things multiplied together, and you have to kind of do some funny business that we do as programmers to play with edge cases and stuff like that. But it turns out the extra stuff that we have in here will be n minus r factorial over n minus r factorial. So this turns out to be the golden formula. And anytime we have n objects and we want to pick r of them in a particular order, this tells us exactly how many ways we can do that. And so this definitely goes on your note sheet for doing homework and for doing the exam. And that's a great formula because it combines the essence of the product rule in a form that we don't have to keep thinking about subtasks. We can just sort of jump to this formula and get our answer right away. So for example, the number of possible hands, including order, of 5 cards from a deck of 52. So, you know, if you play poker, it doesn't matter what order you get your cards in, but if we suppose that the order of the cards is significant, how many ways can we arrange 5 cards picked out of 52? Well, that's just P52, comma 5, which will be 52 factorial over 52 minus 5 is 47 factorial. And there's your answer. Now, if you want to calculate this, right, these are really big numbers. These won't blow up your calculator, but you'll lose a lot of precision. But, you know, this is everything up through 47 multiplied together. This is everything up through 47 multiplied together. Also multiplied by 48, 49, 50, 51, and 52. And that's, you know, just our product rule. But this formula is like nice to just sort of like jump to. Alright, you have 10 runners and 3 medals. You have a gold, a silver, and a bronze medal. And you got 10 people in the race. How many different ways can the medals be handed out to the winners? Well, that's a question of saying how many different ways can we pick 3 people out of the 10 in a particular order. In other words, we're going to pick one person to get the gold medal, another to get the silver, another to get the bronze, right? We're picking 3 out of 10 in a case where the order matters. And that's just a permutation. It's just going to be P10, comma 3, which will be 10 factorial over 7 factorial. How many ways can you sit 6 people at a table? So what would this look like in terms of a permutation formula? Number of ways to sit 6 people at a table.
What kind of table?
Big, long, straight table where everybody's sitting on one side. Because a circular table would change the answer. So how many ways can we do that? Or how can we think of it as a question of permutations?
That'd just be, maybe like 6, 6, right?
Mm-hmm. Number of 6 arrangements of 6 objects, which will be 6 factorial over 0 factorial. So what is 0 factorial, by the way?
1.
Yeah, 0 factorial is 1. That's just one of those things. 0 factorial is equal to 1, just like, you know, 10 to the 0 is equal to 1, even though you're not multiplying it by anything. So number of ways you can arrange 6 people out of 6 is just 6 factorial, so 720. Again, you can think of it as a product rule. First person can sit 6 places, second person could sit 5, third could sit 4, and so on. 6 times 5 times 4 times 3 times 2 times 1. How many ways can you arrange the letters A through H so forget whether they're actually words or not, just arranging those 8 letters?
8 bang.
Yep, it's just the number of 8 permutations of 8 objects. Here's a slightly different question. How many ways can we arrange the letters A through H such that ACE appear in the arrangement right next to each other?
I...
So how could we think about this? Let's not worry about the numeric answer, but let's think about how could we describe this.
Well, there's 5 left over. There's a certain amount of numbers left over for letters other than A, C, and E, which all have their permutations. And then also A, C, E can fit in, what, 3 out of 5, a couple different slots.
Okay, you're in the right direction for sure. Let me rephrase this question. How many ways can you arrange the 6 symbols ACE, comma B, comma D, comma F, comma G, comma H? Because any arrangement of those 8 letters where ACE are next to each other will be an arrangement of these 6 symbols. And the number of ways you can arrange 6 objects taken from 6, that's just P6, comma 6. So this is an example of a question where sometimes you can rephrase it as a different question that will actually be more straightforward. And if we think about putting in 8 letters and then counting how many of those have ACE next to each other, we can get to the solution, but it's a lot of work. But, you know, let's just change the wording of the problem. And let's just say, hey, we've got 6 symbols, these letters, and this weird symbol that looks like ACE. And we're just trying to find arrangements of those where the order matters. Well, that's just back to P6, comma 6. Alright, so a lot of these questions are about thinking about the problem. One big challenge is going to be knowing, you know, what are we arranging, how many of these are we picking, but also, you know, identifying if the order makes a difference. And in all of these examples, the order made a difference. But there's another class of problems called combinations where we're not interested in the order. And so a combination is an unordered arrangement. And this is counterintuitive because combination locks, the order of the numbers matters, right? But mathematically a combination is an unordered arrangement. So your combo lock in high school should actually be called a permutation lock. So this is backwards from our common use of the word. So for example, let's pick 3 people from a group of 4. So how many ways can you pick 3 people from a group of 4 if we don't care about the order in which we pick them? We're just choosing 3 people, But it doesn't matter if I choose, you know, person A before person B or after. It's the same choice. So think about it intuitively. How could we answer this question? How many ways can we pick 3 people from a group of 4? What are your thoughts on this?
Isn't this the same thing, or just... Oh, an unordered arrangement.
It's unordered, and that's going to make a difference.
So you can use the same thing twice.
You can't pick somebody twice, but for example, if I pick ABC, or I pick ACB, or I pick CBA, that's all the same choice of 3 people. But if I pick ABD, that's a different set of 3 people. If I pick BCD, that's a different set. If I pick ACD, that's a different set.
So it'd just be...
So all of those choices represent the same group of 3 people. But here's a question that we can rephrase differently. We're trying to pick 3 people out of a group of 4, right? Well, that's equivalent to pick 1 person to not be chosen. If I'm trying to choose 3 people out of a group of 4, I can do that by simply deciding which 1 person I'm not going to choose. Because I got 4, if I'm going to pick 3, there's going to be 1 person I didn't pick. So how many ways can I pick 1 person out of 4 not to be chosen? There's just 4 choices. Pick person A, B, C, or D. So that's another example of sort of rethinking the problem that gets us really quickly to the idea that, hey, the number of ways we can do this is 4. But that's just a trick. That's not going to work in general. But let's think about, you know, looking at some of the actual choices that we can make. So if I pick A, B, C, right, so I can see my 4 choices by choosing somebody not to pick. Here I'm excluding D, here I'm excluding C, here I'm excluding A, and here I'm excluding B. And so these are the 4 ways that I can pick 3 people. But if I paid attention to order, right, I would see that there are a number of possibilities. Right, all of these arrangements of ABD correspond to that same choice of 3 letters ABD. And the same thing here. I've got those possibilities. And for A, C, and D, I've got some other ways that I could write this. I could do ADC, I could do CAD, CDA, DAC, and DCA. So what's happening here is that I'm looking at the number of ways I can arrange 3 items out of 4. Right, that's P 4, 3, right? P4, 3 is going to be 24. There's 24 ways I can arrange 3 objects out of these 4. But a lot of these choices in here are going to be the same. All 6 of these are going to count as 1 combination. All 6 of these are going to count as a second combination. And so how many different ways can I rewrite this particular solution of 3 people? How many different ways can I arrange that? Well, that turns out to just be 3 factorial. So the number of combinations of 3 things taken from 4 is the number of permutations of 3 things taken from 4 divided by 3 factorial. So let's formalize that. C of n comma r equals the number of r combinations of n items, which is the number of unordered arrangements of r items from n. So this combination n comma r, that's the number of unordered arrangements of r items taken from n. Well, that's the number of ordered arrangements of r items from n divided by the number of orderings of r items. In other words, if we want to know how many unordered ways we can pick r things out of n, let's take how many ordered ways we can do that and divide by the number of possible orders. For example, in this case, if we pay attention to order, the number of ordered ways we can pick 3 out of 4 is 24. But the number of ways we can arrange each of our 3 items is 6. So 24 divided by 6, that gets us our 4. And so our formula for CNR is going to be just P n comma r divided by r factorial. And if we use our formula for what P of n comma r is, this is going to be n factorial over n minus r factorial times r factorial. And so this is our formula for combinations. N factorial over n minus r factorial times r factorial. And so that you definitely also want to put on your favorite answer sheet. So let me write these down so we can refer to them. Right, so ordered is n factorial over n minus r factorial. Unordered, we also divide by r factorial. That cancels out the multiple orders that are included in the number of permutations. We also have another way of writing this, and this is peculiar notation. It's n on top of r inside parentheses. And pay careful attention to that. It's not n divided by r. There's no line in between them. This is a completely different notation. The notation is two numbers, one written above the other inside a big pair of parentheses. That means the number of r combinations of n objects. And that's a standard notation you'll see all over the place when you look at this topic.
Is there a name for this?
So we call this choosing. So n choose r. And that's probably the closest thing to a name for this. So now we can ask some proper questions about poker. So poker, you have 52 cards. You give each player 5 cards, and the order in which they get their cards does not matter. In fact, when they get their cards, they'll probably rearrange them in their hand to their personal taste. So how many poker hands are there? This is 5 cards out of 52, and it's unordered. It's just going to be 52 choose 5. which if you wanted that as a number would be 52 factorial over 47 factorial times 5 factorial. So it's a big number. It's not quite as big as this. In fact, it's 1/120th as big as this because you're dividing by 5 factorial. It's slightly remarkable that this is even guaranteed to be an integer, but it is. But I don't know of a good intuitive reason why that should be the case. So we can go back to our question that we started with. Pick 3 students from a group of 4. That's going to be 4 choose 3, which is 4 factorial over 3 factorial times 1 factorial, which is 4 factorial over 3 factorial, 24 over 6. That's equal to 4. So our intuition for 4 was correct for that. Pick 5 people from a group of 10 people. How many ways can you do that? 10 choose 5. 10 factorial over 5 factorial times 5 factorial. So once you know if you're working with an ordered or an unordered combination, these questions are often just a matter of applying the right formula. But sometimes knowing is it ordered or unordered, that can be tricky. And sometimes it's not worded in exactly that same way. And so here's an example related to bit strings, because we love working with bit strings.
Speak yourself.
Yes. Example, how many n-bit strings contain exactly R ones? So like 4-bit strings, for example. We could ask how many 4-bit strings contain exactly 3 ones. And that might be a useful thing to know. So can anybody think of a way to describe this in terms of combinations? This is pretty slippery.
I think I can see of a way this could be done, but I can't get it in my brain.
Okay, so let's think about this. An n-bit string. Suppose we got a 4-bit string and it's going to contain some ones, right? We can describe the string by saying, which of these positions do we choose to have a 1 in? And for example, this number 0011, I chose to put a 1 here and here. This number 0100, I chose to put a 1 here. If I want a string containing exactly 2 ones, what I'm doing is I'm choosing 2 of these positions to put my 1s into. I could choose these 2, these 2, these 2, these 2, these 2, these 2, right? So 4 choose 2 equals the number of 4-bit strings with 2 1s. Does everybody see that?
Yeah, that makes sense.
If I want a string containing 3 ones, I can describe such a string by simply deciding which 3 of these numbers I'm going to choose. I've got 4 positions, I'm going to choose 3 of them to contain ones. The order doesn't matter. If I say I'm going to put my ones here, here, and here, I get the same number as if I say I'm going to put my ones here, here, and here, or here, here, and here, or here, here, and here, right? It's the same number. So the order in which I choose these 3 positions does not change my answer. So I'm looking at the number of unordered ways I can choose 3 objects out of 4. That'll give me the number of 4-bit strings containing 3 ones. But this is an interesting question to play with. It's a particular question, but let's think about this. So let's continue with 4-bit strings. And let's look at 4(2) equals the number of strings with 2 ones. Well, how many 4-bit strings could I have with 2 zeros? Wouldn't my calculation be exactly the same? I choose which 2 of these 4 I want to put my zeros in.
Yeah.
So that's also the number of the strings with 2 zeros. 4(1) equals number of strings with 1 1. Right? I choose one of these to have a 1. Well, if I have a 4-bit string with a single 1, that's a string with 3 zeros. Right? Because it's a 4-bit string. If it's got a single 1, it's also the number of strings with 3 zeros. But if I look at this question from the original question of how many 4-bit strings can I make with 3 zeros, I would say that's equal to 4(3). So without doing any math, I've just convinced myself 4(1) and 4(3) are exactly the same. They must have the same value. And if I look at my formula here, this is not surprising. Because what is 4(1)? It's 4 factorial over 3 factorial times 1 factorial. If I look at 4(3), that's 4 factorial over 4 minus 3 is 1 factorial times 3 factorial. Well, this and this are exactly the same thing. But from the point of a string containing n bits, the number of n-bit strings containing r1s will be the same as the number of n-bit strings containing n minus r zeros. And so this formula is always going to be true. And I didn't get it by doing any math. I did it with a thought experiment, an interpretation of this combination function. This is the number of strings with r1s. This is the number of strings with n minus r zeros. Well, an n-bit string with r1s has n minus r zeros. So these are describing exactly the same set of strings, and so the number of those must be the same. I put my evil line in the middle there. You didn't see that. And if you go back to the formula, right, you'll see why this is coming out the same as that. Because this is becoming r, this is becoming n minus r. But there's a symmetry in the choice function. And we're going to play off of that in a little bit after a break. There's one other observation we can make here. So what's the choice function that would tell us how many n-bit strings contain 0 ones? 4-bit strings containing 0 ones. What's the choice function? Oh, my camera froze like eons ago, apparently. So number of 4-bit strings containing 0 ones. How can I write it as a choice function? Alright, at least let me know if my microphone's still working.
Yeah.
Okay, cool.
Sorry.
Alright. Alright, so this is the number of 4-bit strings with 2 ones. Right, we're choosing 2 of these positions to contain a 1. So if I want to choose none of these positions to contain a 1, what's the choice function that says how many ways I can choose 0 things from 4?
Would it just be 0, 0, right?
It'd just be 4, 0. 4 things and we're choosing 0 of them.
Oh.
So that's the number of 4-bit strings with 0 ones. How about the number of 4-bit strings with a single 1? What would that look like?
4 choose 1.
4 choose 1. Now you got a number of things with 2 bits. Number of 4-bit strings with 3 bits. Number of 4-bit strings with 4 bits. Well, if I pick any 4-bit string, it's going to contain either 0, 1, 2, 3, or 4 ones. Is there any other possibility?
No. Yeah.
So the total number of ways I can count up my strings with 0, 1, 2, 3, or 4 ones. That sum should be the number of 4-bit strings, which is 2 to the 4th. And if I actually calculate these, I'll find out this sum is exactly equal to 16. And if I go back to thinking about n bits, this is always going to be equal to 2 to the n. And that's kind of bizarre, right? Because what are each of these choice functions? It's a quotient of, a factorial divided by a product of factorials. But here's a formula where I can take the sum of all of these and I end up with just good old power of 2. And that's guaranteed. And trying to prove that explicitly by using the notion of factorials, not obvious how to do that. But from thinking about this as describing numbers of n-bit strings containing r1s, and if I add up the number of strings containing 0 ones, 1 1, 2 1, all the way up to n ones, that must cover all possible n-bit strings, and I know from previous exercises that I have a total of 2 to the n n-bit strings. So this sum must equal 2 to the n, and in fact it does. Alright, so let's take a break, and then we're going to come back. We're going to look at this in application to multiplying polynomials, binomials in particular. We'll look at something called the binomial theorem that you may have encountered in an algebra class. If not, this will be glorious because it's a cool theorem. And then we'll go from that to something called Pascal's triangle. And that will be our culmination of our counting unit. So let's take a break. Let's come back at a little over 5 minutes. All right, I'll see you back here. Snappy nap. How's your mom? Not good.
Oh, you're on a break in?
For another 15 seconds.
Yeah.
Alright, welcome back.
Howdy.
Howdy. Alright. Questions?
You think next term will be in person?
I think so. So my hope is that my in-person 223, I'll be able to do that in person. Because I'm feeling like numbers are dropping to a good point. But I gotta say, if Clark decides, for example, that they're not going to require masks, I will probably stay remote. Or if they decide to do away with social distancing, I will probably stay remote. But if things are the way they are right now, if numbers continue to drop, and if we're going to continue with the same protocols at Clark, my hope is that my Engineering 250 class will be in person, my 101 class will be in person, and the version of 223 that's listed as in person will be, in fact, in person. But we'll see what happens over the next few weeks. So homework, yeah, I'm going to post homework on Wednesday. That will be homework that covers this stuff we're finishing today on counting. And we'll also cover the next unit, which is automata theory. That'll be due a week from Wednesday, which is our last class. And so I'll get answers and feedback posted on that as soon as possible after it's turned in, so that you have at least 1 or 2 days to come into office hours and ask about questions on those. But we'll certainly go over the homework next Wednesday and address any questions there as well. And next Wednesday will be pretty much a wrap up for the course. All right, other questions? All right, let me talk about binomials, and I don't want to get bogged down in a algebra discussion on this. I want to give you kind of the general idea of this, and just kind of like work with it, sit with it, and see if it makes sense. And I'm not going to ask you about the binomial theorem on the exam, but I want you to have seen this because it's another application of combinations. And this comes out of, for example, let's just look at x plus 1. And we know if we raise this to 0, we just get 1, because anything to the 0 is 1. If we have x plus 1 to the first, that's x plus 1. X plus 1 squared is x squared plus 2x plus 1. X plus 1 cubed is x cubed plus 3x squared plus 3x plus 1. I'll do one more. X plus 1 to the fourth is x to the fourth plus 4x cubed plus 6x squared plus 4x plus 1. So how do we know these? How do we quickly figure out what x plus 1 to the n is? And if we write out, x plus 1 to the fifth, we know it's going to be something times x to the fifth plus something times x to the fourth plus something x cubed plus something x squared plus something x plus something. And we don't necessarily know what goes in these blank lines. But let's think about what this means, x plus 1 to the fifth. And you know how to FOIL polynomials, right? First, outer, inner, last. Let's think about a 5-way FOIL. Let's think about multiplying these 5x plus 1's all together. And when we do this, there's a number of different ways we can do this. For example, I could pick the first. I could pick first, last. I could pick the first, last, first. There's a lot of different ways I can do this. And I add all of those together, right? The way that our usual FOIL works. I pick the first of each one, x times x. I pick the first and the last. I pick the last and the first. And I pick the last and the last. And so that's where I get x squared plus 2x plus 1. Well, if I got 5 of these, I'm going to pick, you know, either the first or the last from here, the first or the last from here, and here, and here, and here, and multiply them together. And all of those are going to get added up. Now, I don't know what I'm going to get in front of my x to the 5th, but it's going to be what I get when I add up all the different ways of picking things out of these 5 terms, such that I end up with 5 x's. All right. Well, let's look at one of these middle terms. Let's look at x cubed. Now, if I decide to take x times x times x times x times x, I'm going to get an x to the 5th. That's not going to affect my coefficient here. If I pick 1, 1, 1, 1, 1, I'm going to get x to the 0. That's not going to affect my coefficient here. But how could I pick x's and 1's from these 5 terms so that I end up with something times x cubed? Well, I could, you know, do x, 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 and then 1, 1. And that would give me an x cubed. I could do x, x, 1, x, 1. And I'd have picked an x from these 3. That would give me an x cubed. I could pick 1 from here, and then x from these 3 terms. That would give me an x cubed. So the question of what coefficient goes in front of x cubed is also the question of how many different ways can I choose 3 of these 5 terms to take an x from? Okay, that's the link between binomial multiplication and combinations. The number of ways that I can pick x's or 1's from these that end up giving me an x cubed in the front is exactly the same as how many ways can I choose 3 of these 5 terms that I'm going to take an x from. And that's just 5 choose 3. If I want to know how many different versions of picking either an x or a 1 from each of these will leave me with a coefficient in front of x squared, it's the number of ways that I can choose 2 of these 5 things to pick an x from. And so this is going to be 5 choose 2. And this will be 5 choose 1, and this will be 5 choose 0. And this will be 5, 4, and this will be 5, 5. And so if you want to know what x plus 1 to the 5th is, if you know what these choice functions are for r things chosen from 5, those are the coefficients of these powers of x. And so this is 1, 5, 10, 10, 5, and 1. So is this something that you've seen in your algebra classes before? This so-called binomial theorem?
Never.
Never?
This is like linear algebra, right?
Not necessarily. I'm not sure this gets covered in the linear course.
Yeah, never seen this.
Okay, well I'll give you the more general form because it's useful. So x plus y to the n. So your monomials are going to be x to the n minus 1 y, x to the n minus 2 y squared, x to the n minus 3 y cubed, dot dot dot, x to the 2, y to the n minus 2, x, y to the n minus 1, and y to the n. and you've got coefficients in front of here, and you add these all together. These coefficients will be n choose n, n minus 1, n choose n minus 1, n choose n minus 2, all the way down to n choose 0. And so we could write this in a nice little formula. X plus y to the n equals the sum from I equals 0 to n of n choose I, x to the I, y to the n minus I. And that's a nice little formula. Not going to be on the exam, right? Don't need to put it on your answer sheet, but you know, desert island scenario, it could help you. 100 angry monkeys coming at you wanting bananas. You can maybe use the binomial theorem. And it's also interesting because, you know, remember, these choice functions, these are like ratios of factorials. Doesn't seem like it would necessarily have something to do with multiplying a bunch of binomials together and foiling and all that kind of stuff, but it does. They're closely related. And we noticed this symmetry business where, you know, n choose r was the same as n choose n minus r. Well, that tells you that, you know, these opposite terms are going to have the same coefficient, right? There's a 1 there and a there. There's a 4 there and a there. There's a 3 there and there. There's a 1. There's a pair of 5s. There's a pair of 10s. And that should make sense to you, because we also know that x plus y to the n is the same thing as y plus x to the n. Well, that right there, since this is going to be the same as that, it tells me that, you know, whatever I get for x to the a, y to the b, I got to have the same coefficient for y to the a, x to the b. There's got to be symmetry here. So that's kind of a observation slash motivation slash springboard to something called Pascal's triangle. Not triangle, but triangle. And Pascal's triangle is this cool little thing. Pascal, French mathematician, studied probability and physics, I believe, and a number of other things. Here's Pascal's triangle. So here's one way to write this. Start with the number 1, and then right below it, write a pair of 1s. And each row of this triangle is going to begin and end with a 1. That's one of our rules. But each spot in the middle is going to be the sum of the two things above it. So 1 plus 1 is 2. Alright, next row I'm going to write a 1 on each end. 1 plus 2 is 3, 2 plus 1 is 3. There's the fourth row. Fifth row, put a pair of 1s on the end, and then each term in here is the sum of the two terms above it. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. And you can just keep doing this. 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5. And one thing to note is that these numbers that we're writing down in this triangle, these match the coefficients for a binomial expansion. 1, 4, 6, 4, 1, 1, 4, 6, 4, 1. 1, 3, 3, 1, 1, 3, 3, 1. 1, 2, 1, that's x squared plus 2x plus 1. And if we accept that, you know, these coefficients of this binomial expansion are choice functions, these must be the value of choice functions. And so if you go down to the nth row and the rth term, the value there is just n choose r.
Quick question.
Yeah.
Would this also work in, like, say, outside of x plus 1? Could it be like x plus 5?
Yeah, so we can generalize this to x plus y. X plus 1 is a simpler case just because the powers of 1 are just 1. But we could do this to, you know, x plus y cubed is going to be x cubed plus 3x squared y plus 3xy squared plus y cubed. Now if y is 1, then the y's just go away. But yeah, it works in general. All right, so Pascal's triangle, we know that each term here is the value of a choice function. You go down n, you go across r. That's the choice function you get there. So let's start looking at other properties here, and let me fill this out a little more. And once you start doing this, it's hard to stop. There was some talk on Discord earlier. In past years, I've given a programming assignment in this class to write a program that prints out Pascal's triangle, and it's pretty straightforward to do because you start with a 1, you take the two things above you, you add them together, that gives you your next term. So you just save each row. And then to calculate the next row, you use that previous row that you saved, just add them up, successive elements of that array to get the elements of your new array. Save those, go on to the next one, just keep going. So it's hard to get it to look like a triangle, but to get the numbers, not too bad. So what if we add up each row of this structure? So 1 is just equal to 1, 1 plus 1 is 2, 1 plus 2 plus 1 is 4, 1 plus 3 plus 3 plus 1 is 8, 1 and 4 is 5, 6 is 11, 4 is 15, 1 is 16. What's the pattern here?
It doubles every time?
It doubles every time. Exactly. So each row adds up to the next power of 2. And this is this thing that we alluded to a while ago, that, if we think of say, a 6-bit string, this is the number of 6-bit strings with 0 ones, 1, 2, 3, 4, 5, or 6 ones. And the sum of all of those would be the number of 6-bit strings containing any number of 1s. Well, that's exactly the number of 6-bit strings, which is 2 to the 6th, which is 64. So all of these had better add up to 64, which they do: 20, 50, 62, 64. We've got symmetry about this axis because the number of r combinations is the same as the number of n minus r combinations. If you like, we're choosing r things out of n to include. We're choosing r things out of n. To include is the same as choosing n minus r things out of n to exclude. So we've got to have this symmetry. So that's good. Well, let's look at some weirder stuff. Suppose we add the square of each element on each row. So 1 squared is just equal to 1. 1 squared plus 1 squared is equal to 2. 1 squared plus 2 squared plus 1 squared. Well, 2 squared is 4 plus 1, 1. That's a 6. 3 squared is 9. 1 plus 9 is 10. Plus 9 is 19. Plus 1 is 20. We'll go one more. 1 squared plus 4 squared is 16. That's 17. Plus 6 squared is 36. Plus 4 squared is 16. Plus 1 is 17. 17, 36, and 17. That comes out to 70. If we add the square of each number on each row, we get a 1, a 2, a 6, a 20, and a 70. Can you see where those come from the triangle? Do you see those in the triangle?
In the middle?
They're right there in the middle. There's the 1, the 2, the 6, the 20, the 70. So the sum of the numbers in row R is equal to the middle number of row 2R. Kind of cool. All right, here's another property. If you ignore the ones on the sides, right? Let's just look at row P. So here's row 1, row 2, row 3, row 4, row 5, and so on. All right, let's forget about row 1. Row 2, every number other than the ones on the end is divisible by 2. There's only one number in the middle, that's a 2. So row 2 has this property that every middle number is divisible by 2. Row 3, well, the only middle numbers are 3, so every middle number is divisible by 3. But row 4, here's a number in the middle that's not divisible by 4. Row 5, every middle number, 5 and 10, is divisible by 5. Row 6, well, 15 and 20 are not divisible by 6. Row 7, all of these numbers in the middle are divisible by 7. Row 8, not the case, right? 70 is not divisible by 8. Let me see if I can go one more. This will be embarrassing. I made it. Row 9, not all of these numbers are divisible by 9. 126 is not divisible by 9. So the rows where every internal number is divisible by the row number look like 2, 3, 5, 7, but not 9. And I'll give you a hint, the next row where this works is row 11. So what's the relationship between those rows, 2, 3, 5, 7, and 11?
Prime.
They're prime numbers. And that's a cool little fact buried inside Pascal's triangle. If every number on a row P, other than the ones on the end, is divisible by P, then P is prime. And that's the only case where that fact is true. And if P is not prime, there'll be at least one number in the middle that's not divisible by P. So we got prime numbers buried inside here.
Also, there's the hockey stick thing.
There's the hockey stick thing. And there's square numbers. So this is 1. This is 1 plus 2. This is 1 plus 2 plus 3. 1 plus 2 plus 3 plus 4, and so on. There's Fibonacci numbers buried in here. Take a look at this number right here. If we just read across each row and think of it as a number, this is the number 1. This is the number 11. This is the number 121. This is the number 1,331. And this is the number 14,641. Is there a connection between these numbers? Is there a formula for these? Anybody see anything?
Fibonacci?
Not exactly. Something simpler. Something more straightforward at least. 111, 121, 1331.
I have no idea.
That's
Is it
fair.
just that it's like a reversing pattern?
It is. There's a reason. These are all powers of 11.
That's weird to think about.
Yeah. What's even weirder is the next number in here. Looks like 1, 5, 10, 10, 5, 1. Well, that's not a number. 10 is not a digit. But if we were working in, say, octal, and we wrote these down, you know, with A's in here, right? if our base 10 allowed us to write a 10, or if you're learning how to multiply and you're learning to change, you know, something 1 beyond a 9 to a 10 so you can work with it, this would end up being 11 to the 5th. And so this pattern actually holds, but the way we write decimal numbers sort of defies that pattern beyond 11 to the 4th. But it holds, and that makes sense with this idea that each number here is the sum of the two numbers above it. If you take a number and you multiply by 11, well, each of these is the sum of, each digit here will be the sum of the two numbers that were above it. This will be the A plus B, this will be the B plus C, and so on. And that's the touchy-feely explanation of why this is happening. And so that's pretty cool. Alright, I used to have a PDF of this, but I'll just take it from the web. Let's see. Okay, yeah, this is a good one. So, so properties of Pascal's triangle. So this is the one that, you know, the first number divides everything else on the row, only for the prime rows. Sum of each row gives you a power of 2. The magic 11s. The hockey stick pattern. So if you start at any point on the edge and you move down in one direction and then you jog left, the number you get to is the sum of all the numbers that you travel to in the first direction. And so that's kind of cool. Triangular numbers, sum of consecutive integers, just come down this diagonal or down this diagonal was the one I picked on. Square numbers, so well, that's the same thing. Fibonacci sequence. So if you start from any point and you add up on these diagonals, you get Fibonacci numbers. And anytime you do something and you end up with Fibonacci numbers, you know it's a good day, right? There's something good going on. And there's other things in there, right? How many ways you can split a polygon into triangles, and that's called a Catalan number, and Catalan numbers are contained inside here. I have no idea why these things are. There's the binomial expansion. And there's self-replicating shapes. So how many people here are familiar with fractals? Let me see a thumbs up or hands or shout out a yay.
Heard of it, but I don't know what it is.
Fractals are the idea of patterns that contain themselves. And it comes from the idea of, you know, if you draw a map of the west coast of the United States, right, and it looks like this, and you can take a piece of dental floss and measure it and hold it up against the scale of miles, you can get an approximation for the length of the coastline, right? If you go out and you drive along a road that goes along the coast, you can measure on the odometer of your car a better estimation of what the mileage is. Or you can go down with a tape measure and you can start measuring, you know, along each rock as you go from one point on the coast to the other. And the more precisely you do this, the bigger a number you get. And if you were to go down and you were trying to measure every single little crevice and every single stone along the coast, your numbers just get bigger and bigger and bigger. And so the idea that, you know, the distance from here to here is finite, but the length of this line could approach infinity, that's an idea of fractals. This is not on the exam. But here's the classic example of a fractal. Take an equilateral triangle. and cut each side into thirds. So now you have a little segment that's 1/3 the original size, and draw an equilateral triangle there. And now take each of these sides and cut it into thirds. And the middle third is, 1/3 the size of the previous size you used. And draw a little equilateral triangle there, with each side being the same 1/3. And keep doing that. So you get a series of shapes, and each shape has more of these little spiky things on it, and the spikes get smaller, but you have more of them. And write an expression for the total length, the total perimeter of this shape. And no matter how many times you do this and how many little spiky spikes you add, this shape is always contained inside this box. So the area is finite. But as you continue doing this, the perimeter approaches infinity. It grows without bounds. And so here's a shape that you can draw that has finite area but infinite perimeter. And that's just kind of a weird thing, right? That this single shape never doubles back on itself. It's just the outline of this, very complex polygon. The area gets longer and longer and longer, but the length gets longer and longer, but the area is always finite. And so normally we think of dimension as, here's a line. If we double the length of the line, we double the length of the line. Here's a square. If we double the length of an edge, we quadruple the area, right? Double this, the area goes up by 4, which is 2 squared. If you have a cube and you double the length of an edge, the volume goes up to 8, 2 cubed. This exponent is why this is a 3-dimensional shape, this is a 2-dimensional shape, this is a 1-dimensional shape. With these things, the ratio of perimeter to area is fractional, and so they're called fractals. That has nothing to do with anything on the syllabus, but if you don't come out of Clark having at least heard the word fractal, you've been ripped off. So now you got your money's worth. So that's one of the properties inside Pascal's triangle. If you look at the even numbers, they have this fractal shape related to this triangle I just drew. Fractals are related to self-repetition. If you have this shape and you zoom in and look at one little section of it, you cannot tell how far you're zoomed in. You can't tell if you're looking at this part or something where you're zoomed in like a million levels. It's going to look exactly the same once you remove the notion of scale. So it's sort of self-repeating. That's another property of fractals. All right, all of which is unrelated to counting or permutations and combinations, but serves as a segue from what we just finished talking about to what we're going to talk about next. So any last questions on the counting discussion? Product rule, sum rule, pigeonhole principle, permutations, combinations. I'll post some problems probably tomorrow. We'll talk about them Wednesday, but it'll be, questions like what we've been doing. Here's 15 people, and you're picking 6 of them to do such and such, and so how many ways can you do that? That sort of thing. All right, well, let's move on. So I think in the syllabus we're supposed to talk about graph theory next. But, we lost a week of classes because of the Monday holidays. So I'm thinking I'm going to do graph theory in CSE215 because we'll have good application for some of the concepts there. And so I'm going to skip on to the what's listed as the last unit in the syllabus, and this is going to be languages and grammars. And we'll definitely talk about this on Wednesday and possibly part of next Monday also. And so, you know, language has been studied for a long time. Language is how we communicate. It's what we're using right now. There's written languages, there's spoken languages, there's symbolic languages, there's computer languages. Language is a way of conveying information. And one of the things that people have studied is, you know, what makes up a language? What do languages have in common? And so linguistics is a whole area of study. And what we're going to talk about here is sort of a systematic treatment of how to decide, how to describe a language, right? In particular, how do we describe what would constitute a legal sentence inside a language, right? And we're going to make a strong distinction between syntax and semantics. So semantics is the meaning of something. The syntax is just the structure of something. And we're only going to focus on syntax. So this is an area where, for example, if you were designing a language and trying to write a compiler for it, you would be interested in the syntax of the language. Semantics would be the meaning, and let me give you an example. All right, here's some C code. Syntactically, this is absolutely fine. I can put this into a compiler, it will compile, I won't even get a warning. So the syntax of this relative to the language we call C, absolutely fine. This is valid sentences inside the C language. But the meaning, the semantics of this set of code is kind of ridiculous. What this code is saying is see if 1 is equal to 2, and if it is, add 0 to x, subtract 0 from x, and then do some loop as long as x is bigger than x plus 1. Right? Well, 1 is never equal to 2. Adding 0, subtracting 0 does nothing, and x is never bigger than x plus 1. So this whole thing is going to generate code that, you know, none of this is ever going to happen. It's ridiculous. But syntactically it's fine. Okay, and we're going to be studying syntax, not meaning semantics, but structure, syntax. And so we're going to think about formal languages. Now, English is not a very formal language. If you're not a native English speaker, you've probably got recent experience with how weird English is, right? But if you learned English when you were first in school, you may remember, you know, some of the weirdness about English. But I think when you're a kid, it doesn't seem as weird because, you know, everything seems weird. But English has all kinds of weird things to it. Things that don't follow rules, right? Why do you put an S at the end of some words to make it plural, but other words you don't? Right?
Why
So
goose, not geese? Say
what?
Why geese, not gooses?
Exactly. And so English is not really a formal language in that sense, but I'm going to pick on English as an example. And I'm going to, you know, describe a very small subset of English and try to make it more formal, just as an example. So I'm going to define a sentence. I'm going to say a sentence is what I call a noun phrase followed by a verb phrase. Alright, so sentence is a noun phrase followed by a verb phrase. A noun phrase is going to be an article followed by an adjective followed by a noun, or, so I'm going to use a pipe to mean or, it's going to be an article followed by a noun. An article is like the, one of these little words that we use for an introduction. A verb phrase is going to be a verb plus an adverb, or it's just going to be a verb. Adverb is the thing that modifies a verb. Adjective is the thing that modifies a noun. So big house, run quickly, that kind of thing. So I'm trying to define what a sentence is in this language, and so far I'm describing it in terms of other things. A sentence is a noun phrase followed by a verb phrase. A verb phrase is a verb followed by an adjective. At some point, though, we've got to get down to actual, words if we're going to actually try to form a sentence, or look at a set of words and say, is it a sentence? So these are, defining one thing in terms of other things. You can start to think about recursion at any point if you like. We need some base cases. So my base cases are actual words. So for example, an article is going to be either a or the. An adjective is going to be either large or hungry or funny. A noun is going to be either a rabbit or a teacher. A verb is going to be hops or eats or speaks. And an adverb is going to be quickly or wildly. Alright, so here's a definition of a formal language. And in this language, we have sentences, and the sentence is a noun phrase followed by a verb phrase. Well, what's a noun phrase? For example, it's an article followed by a noun. What's an article? What's a noun? It's a rabbit or a teacher. Alright, so we can do two things with this, right? One thing we can do is we can use this to build sentences. So we can say, a sentence is a noun phrase followed by a verb phrase, and a noun phrase could be an article followed by an adjective followed by a noun, and a verb phrase might just be a verb, and an article could be the, and an adjective could be large, and the noun could be rabbit, and the verb could be speaks. And we have a sentence, the large rabbit speaks. Is that a valid sentence? Yes. It's valid because these things constitute a noun phrase, and this constitutes a verb phrase, and a noun phrase followed by a verb phrase constitutes a sentence. So we can build sentences like this. This is what Mad Libs is, right? You get how many people have done Mad Libs?
I've done Mad Libs. They're awesome.
Awesome, we got some thumbs ups. Yeah, Mad Libs are basically, it's a book, and it basically says, give me an article, give me a noun, give me a verb, that kind of thing. And one person is reading these, and the other person is giving them words. and you fill these words into the sentences, and then you read back the story that you've got, and it usually comes out goofy because you don't know what the context is, but it comes out as a syntactically correct story. It's a set of sentences that are guaranteed to be correct sentences because you filled in the right types of things, but the meaning ends up being really bizarre. So we can build sentences with this, right? We can construct things that are recognized by this formal language, things that are sentences in this formal language. But, you know, with syntax correct, but maybe a questionable meaning, like the large rabbit speaks. Well, most large rabbits don't speak, right? They don't need to. But nonetheless, it's a valid sentence. The other thing we can do is we can use this to check syntax. So if we have a sentence like, you know, a hungry teacher hops quickly, we can say, is this a valid sentence? Well, if you've ever diagrammed sentences in school, this is sentence diagramming, right? We could take this and we could say a hungry teacher, and this is a noun phrase, and hops quickly, this is a verb phrase. And we could break this into an article, an adjective, a noun, an adverb, and a verb. All right, so that's one example of a formal language, but it's not one that's terribly usable inside a computer. Right. Well, sometimes we'll write things like this. We'll talk about something called BNF later, that looks kind of like this actually, and is usable. But for kind of studying the question of language and what's a sentence inside a language and so on, we want something that we can make more formal. And so we've got about 10 minutes left. Let me give you some definitions. And then we'll build on these on Wednesday to come up with a precise way to describe what we're going to call grammars, which will be formal languages. So let me just give you some definitions, and then we'll start using these on Wednesday. So a vocabulary, V, is a finite non-empty set of symbols. So vocabulary is a finite non-empty set of symbols. A word, or sometimes a sentence, over V is a finite length string of elements of V. So we could think of our vocabulary as being letters, and a word over that vocabulary being a finite length string comprised of those letters. Or we could think, a little more keeping with the way these terms sound, our vocabulary could be a set of words, and a sentence over that vocabulary is just a finite length collection of those words. But we don't necessarily need to map this to English, and we're going to use what we're building here in a very different context from thinking about English sentences. We're going to think about this as a more general concept of languages. So we don't need to, you know, make precise the correlation between these terms and English, but we will think about that sometimes. All right, so there's a special string which is lambda. This is the empty string. And this is not an empty set. It's not a set, it's a string, right? It's a string that happens to have length 0. So this is also called a null string. So a word is a finite length string of elements of V. It's possible that, we might take a string of length 0. That's a word, but it's a special word. It's a word with no elements in it. All right, V with a star is a set. It's the set of all words over V. So V star is the set of all words over V, the set of all finite length strings of elements of V. If V was the set of letters A through Z, this would be the set of all different combinations that you could make of letters, as long as the string that you came up with was finite length. All right, it's not an arrangement or a permutation because you could include things more than once. It could be the empty string. It could be a string containing an H followed by an E followed by two L's followed by an O. This star, by the way, this is the star that you get in grep in Unix when you do regular expressions and you use a star for 0 or more repetitions of something. That's the same star. That's a side note. All right, so here's our definition of a language. A language over V is just a subset of V star. So a language over V is some collection of words over V. In other words, a language over V is some collection of strings comprised of the symbols in this set V, in the vocabulary. All right, so the approximate mental picture I have in mind, V is like a set of letters. A word over V is just a string of those letters glommed together side by side. That's a word, right? V star is the collection of all words of finite length. And a language over V is some subset of that V star. It's some collection of particular words, which are just strings of letters glommed together side by side. In the sense of English, right, this could be A through Z. This could be, just a collection of letters that you bang out on a typewriter side by side. This would be all such strings that you could create. This could be the words that you find in the dictionary. The particular strings of letters that correspond to what we consider to be English words. So the language would be that set of words. All right, so the parting question here is, how do we specify a language? We've got our vocabulary. We know a language is some subset of V star. How do we specify a language? And there's three main ways that we can think about. The first is list rules for a word to be part of the language. So we have a set of rules. Well, do we have that in English? Yeah, we have some rules, right? Every word except syzygy has to contain a vowel. If you have the letter Q, it's got to be followed by a U. And there's other rules, right? They don't work terribly well. They can be used to eliminate some things, right? I know that this is not a word because there's no vowel in there, right? But is abracadabra a word? Well, maybe. So one option is to list the rules. A second option is to list all words. Just make a big table of all the words that are part of your language. Is that a reasonable thing to do?
In the context of the English language, I would hope not.
Yeah, actually, in the context of English, though, it is. It's called a dictionary. And it's bizarre to think about that, but what is a dictionary? It's a list of all the words that are legal in English, which is, really strange. But that's actually what a dictionary is, right? All
Depends on your definition of a language.
Yeah,
And
yeah.
Descriptivism versus descriptivism, that's a whole other thing.
Yeah, yeah. So this would be a horrible thing to do for C. Imagine if your compiler had a dictionary of every possible C program, and when you type in a program and you say GCC, it looks up in the dictionary to see if it can find your program. Well, that would be a terrible way to write GCC. But that's exactly what we do in English. You're playing Scrabble and someone comes up with a 12-character word and you want to know if it's a real word. You go to the dictionary and you look it up and it's alphabetized, right? So rules probably work better for something like a programming language. A list of all words works pretty well for kind of a human language. But neither of these is really great, right? So we're going to concentrate on a third option, and this is where we'll start off Monday, which is where we're going to describe what's called a grammar. And a grammar is going to be a set of symbols and a set of what we call production rules, ways that we can take some starting set of symbols and form words from them. So it's going to be a way to create words from a small set of starting points. And in particular, we're going to study one type of grammar called a phrase structure grammar. And so this is going to get into a bunch of definitions and a bunch of formalism, but we're going to quickly go to working through some examples of phrase structure grammars and see what kind of words are recognized by these. And then we'll move to trying to construct a phrase structure grammar in order to recognize certain sets of symbols. And so much like state machines in our 250 class, we're going to do two things. We're going to do analysis and synthesis. And the first part of this will be analyzing some phrase structure grammars to see what they represent. And then the second part will be trying to synthesize, trying to come up with phrase structure grammars that satisfy certain criteria. And so we'll do that for a bit. We'll look at Bacchus-Nauer form, which is another way to describe languages. We'll visit state machines briefly, just because they tie into analyzing languages. All of this stuff that we're going to be doing with phrase structure grammars is really talking about state machines. We're not going to do previous state, current state tables, so we're not going to do flip-flops or anything like that. But we're going to do a high-level discussion of state machines and look at how we can use state machines to recognize languages. And then we're going to talk about Turing machines. And Turing machines are kind of like why we're here for computer science, right? All the stuff that we do on computers is really based on work that was, done by Alan Turing and others early part of the previous century. And the machine that Alan Turing theorized and used for the analysis of different questions, we call that a Turing machine. That's basically what you've got in your laptop or your desktop or your smartphone. These are Turing machines. It's an architecture that's about 100 years old and hasn't really changed much. And so we're going to study that, and that turns out to be a useful way to study questions about computation. And so that's where all of this is leading, is being able to think about and analyze and pose questions about computation itself. And so we'll be moving into some weird areas related to limits of computation, types of problems that we can compute, and so on and so forth. So all good stuff coming up. We are out of time for now, but we will continue with this on Wednesday. All right, thanks so much.
Thank you.
I'm excited.
Have a good day.
You too.
You have for me.